I'm going to go through this last little step. The bell's going to be ringing here in a few minutes as I'm recording it, so don't let that bother you. But I just want to go through this one really quick. This is now my last going after, it's our second way to go after delta H, but this is the last setup in this whole unit. And it's going after delta H using what we call the heats of formation. That's what I give you the chart for. So the nice part is, all it is simple arithmetic. It's the sum of the products minus the sum of the reactants. If you remember to crisscross your data, you're fine. We talk about heat of formation in specific, it's kilojoules, heat of combustion is kilojoules, but they're specific because they're per mole, and those moles we made a note from, those moles are acquired from the coefficients in the balanced chemical equation based upon what specifically is being formed or combusted, and the problem will tell you what it wants. But before you can get specific, you must first say general, and that's just the heat of the whole reaction, so your answer ends up in kilojoule. As you work through this situation, I will provide you with the balanced chemical equation. I may ask you to know, though, that a combustion reaction, you always react with oxygen as a gas, produce CO2 as a gas, and water as a liquid. But I'll take my products, my carbon dioxide and my water, and I will subtract my reactants from that. That's my methane and my oxygen. So I will give you the values, and as you can see, the moles are not here because I'm assuming already that the coefficients, my balanced chemical equation, have canceled them out. So I take the sum of my products minus the sum of my reactants, and there's my actual delta H. It is a negative value because it is exothermic reaction. I move on to the second one, and now I have, again, this one, I just want the heat of the whole reaction. I have chlorine as a gas, plus 2 HBr as a gas, and 2 HCl is a gas, and Br2 is a gas. And so this situation is the sum of my products minus the sum of my reactants. Now in this situation, I have 2 HCl plus 1 bromine as a gas, minus 2 chlorines as a gas, plus 2 HBr. So in this situation, I brought back in the actual value because the values I give them to you on the test, I will show you because these are the heat of formation values, kilojoule per mole. They are specific. But as we can see, the coefficients are also moles, and so they cancel each other out. I have 2 moles of HCl, so it cancels out. I have 1 mole plus 1 mole of my Br2 as a gas, minus 1 mole of chlorine, Cl2 as a gas. You can see it has a 0 heat of formation because chlorine Cl2 as a gas is its standard state, which is based upon the periodic table at 25 degrees Celsius and 1 atm. And then I subtract from that 2 HBr. I have 2 moles of HBr weighing in at negative 36.2 kilojoules. And so as my moles all cancel out, my answer, I do simple addition subtraction, and I come up with negative 81.3 kilojoules, and this is the exothermic reaction. Remember, sig figs, you're looking at your heat of formation values, and it's just the addition subtraction rule, so you're looking at the least number of digits to the right of the decimal, and those are your sig figs for each problem. Problem number 3, I wanted you to the balanced chemical equation first. We have acetylene. And it goes through delta H subscript C says it's combustion. So I'll always react with oxygen gas, produce CO2 as a gas, and water as a liquid, and then we balance it. I have 2 moles of acetylene plus 5 moles of oxygen yields 4 moles of carbon dioxide and 2 moles of water. So now I want to go after first the heat of the reaction, and then I'm going to get specific and come back after acetylene. So I realize at the very end, we see we have 2 moles of acetylene. I'm just going to take my heat of reaction and divide it by 2. Because I have 2 moles of acetylene in my problem, balanced chemical equation. But first of all, I must get the heat of the whole reaction. I must get the kilojoules before I can become specific. So I take the sum of my products minus the sum of my reactants. So my 4 carbon dioxides plus my 2 waters minus my 2 acetylenes and 5 oxygens. Now remember, O2 as a gas is its standard state, so it's a value of 0. You don't necessarily have to show it if you want to. But again, remember the kilojoules per mole, the moles cancel out because of the coefficients in the balanced chemical equation. So the heat of reaction, the units are just plain kilojoule. Remember that. People always make a mistake in the test when they make a kilojoule per mole. The moles, the coefficients, will cancel them out. So I end up with a negative 2,598.9 kilojoule. Now I want to know specifically per mole of acetylene, so I divide by 2. 2 moles, my balanced chemical equation. Divide by 2, and it takes half that, a negative 1,299.5 kilojoule per mole, and that's of my acetylene. A fourth problem, again balancing propane, C3H8 goes through combustion, reacts with oxygen, O2 as a gas, produces CO2 as a gas, and H2O as a liquid. And then I balance it. It's a 1 mole of propane, 5 moles of oxygen, produces 3 moles of carbon dioxide, and 4 moles of oxygen. So again, I take the sum of my products minus the sum of my reactants. So I have my 3 carbon dioxides plus my 4 waters, those are my products, minus my 3 propanes and 5 oxygens. Again, oxygen is a standard state, has a value of 0. So my 3, I look at my carbon dioxide and oxygen, I will provide those for you. As you can see, I don't even show kilojoule per mole because I just know that my final answer for heat of reaction will be in kilojoule. So I say 3 of my carbon dioxides plus 4 of my oxygens minus a propane, minus negative 103.85. And there's my answer. And it ends up being negative 2,220.0 kilojoules, least number of digits to the right of a decimal. 393.5 as 1 digit, so my answer only has 1 digit to the right of a decimal. But now I want to know heat of combustion for propane. Go back up to the balanced chemical equation. I see that I only have 1 mole of C3H8. 1 is understood, so I divide by 1. So numerically it stays the same, but now it just came more specific because I'm now dividing by moles. My fifth one says, going after the delta H reaction for the following reaction, I see I have 1 mole straight across. I'm just going to take the sum of my products minus the sum of my reactants. So I have 1 water plus 1 sodium chloride minus 1 hydrochloric acid and 1 sodium hydroxide. Look up their values. And I have 1 of all of them, so I add up my water and sodium chloride, and I subtract from that my hydrochloric acid and sodium hydroxide, and I end up with negative 56.1 kilojoule. Exothermic reaction. My 469.6, 1 digit, 407.1, 1 digit, 167.2, 1 digit. So my answer only has 1 digit to the right of a decimal. The last one is easy. It's the heat of combustion of hydrogen. So again, I have hydrogen goes through combustion, means it reacts with oxygen gas. Now my only 2 options are CO2 and H2O. It doesn't mean I'll always get them. As I see, I have no carbon on my reactant side, so I'm not going to get carbon dioxide. Of the 2, I'm only getting my water, so I have H2O as a liquid. In doing this, I have balanced my chemical equation. I take the sum of my products minus the sum of my reactants, and I realize that both of my reactions, H2 as a gas and O2 as a gas, both are red on the periodic table, so they're at the standard state with 25 degrees Celsius, 1 atm, therefore their value is 0. So all I have is 2 waters minus my 2 minus 0, and so I just double my waters, and that's my answer. But then I want to get specific. That's just the heat of the whole reaction in kilojoules, but I want to now get specific. Combustion of hydrogen. So I look only at hydrogen. My H2 is a gas, my balanced chemical equation. I have 2 moles of that, so I divide by 2 and end up with negative 285.83 kilojoule per mole of hydrogen.